So this is going to be almost like an emergency last-minute video, simply for the sake that any students who want to review, again, hearing or listening to any of this, or me just babble, I'm not doing this with any script. So basically a lot of this is off the cuff. I'm going to basically go through the structure of an atom, the quantum mechanical model of an atom. So be prepared. There's no script, etc. I might have a few things that don't flow well, don't sound right. You might hear me pause because I'm going to go look over at the textbook just to make sure that some of the things I'm saying, even I'm going to try and match some of the things that are said in the textbook. So this way, if you read certain sections, so right now we're using 8th edition of Zumdahl, and it's chapter 12. So one of the most important sections in it is the one that talks about the quantum numbers. So in the 8th edition, it looks like 12, section 9. We're talking about quantum numbers. But before that, I'm going to start off with a brief overview of atomic structure. So you could basically say that this would be an overview of the atom, and essentially the idea is the structure of it. So the overview is going to start out by thinking, okay, what has been taught, whether in grade school, high school, etc. I definitely can remember how one of the first models that came up, and strangely enough, I mean, I'm just approximating the date. This could be like 1900-ish. So he basically came up with that plum pudding model where they said, look, we're pretty sure there's a concentrated center of an atom that has positive charge, and somehow, some way, negative charge is around it. And they called this the plum pudding or raisin bun model, or whatever you want to call it. Funny thing about the model was, at the time, the only thing they knew for sure, and I believe it was the gold foil experiment, the shooting alpha particles, and it was only every once in a while that one of them would hit something so dense it would bounce back. So that's how they came up with the idea. There's a very dense central small part of the atom right here, because otherwise these gold atoms fly right through this much less dense stuff. So they figured, you know what, we're going to balance it, we'll call it negative charge. So compared to what you guys deal with now, just only 100 years later, so it's pretty new. We don't think of it this way. Then comes along, let's just say, a popular image that still exists today, where people will say, okay, you got a positive thing like this, and they have these sort of oval shapes like that. And then sometimes you'll even see people drawing little dots saying those are the electrons. So this image now, compared to this one didn't even draw tiny little circles for electrons. They thought of it as negative stuff, right? And the only thing they wanted to draw a circle around was the dense nucleus. So that distinguished it. But this one, they have a distinguished nucleus and these little electrons, that seem to be moving. So this image brings to mind the electrons, those little BBs, are always existing and present as little chunks of mass, right? This is horrible, and this is one that let's not even talk about it, as you'll soon find out why. Then we have the Bohr model and a lot of other books, and when you look on Wikipedia or the history of it, it's closely related to Rutherford. So some of them even called it the Bohr-Rutherford model, and just to shorten it, they're going to call it Bohr. In even the first year university college textbooks still have this, where they call it the planetary model, right? So some will say, planetary model, and then they'll draw these nice circular rings, nicer than the ones I'm drawing, blah blah blah, and this would be sort of your first. This is your second, and this is your third, blah, blah, blah. So what Bohr managed to do, he realized through experiment that it was the change in the energy between these. So he even said, okay, let's just say you have an electron that's in 1. To make it go and be in the second orbit, you're looking at this energy difference. As you could say, it's the energy of the second minus the energy of the first, whatever. You get how many joules of energy is required to either make it go up to the next orbit, or if it fell back down, it would release this much energy. What's even more important, and the reason why it's still taught, is because the one thing that he absolutely did get spot on was how, first of all, the Bohr model, like this one, it worked very accurately, even for experimental results. It worked very accurately for a hydrogen atom or a 1-electron atom. So for example, carbon normally has 6 electrons if it was neutral. But let's say you took all these out. So let's say you had carbon plus 5. Its nucleus would have a positive 6 charge. And then what Bohr basically proved is if you stripped carbon of 5 electrons, 1 electron remaining, you still had these hydrogen-like differences. So his model worked for a 1-electron atom system. Can't stress this enough, folks. 1-electron only systems, whether it's the actual hydrogen atom itself that happens to be neutral or any other nucleus, as long as only all it has around it is 1 electron, then this orbital model, planetary style, and these equations he had for energy differences matched experiments very well. The instant you put a second electron in, everything just went to hell. And this is why there was a big problem. But the number one thing that was really good about this is you had to look at changes in energy between allowable energy states. He was the first to start saying, look, whether you want to have a physical interpretation of orbits like the planet model or not, the one thing, cover this picture up, the one thing they know, differences in allowable energy states is what can be measured experimentally without question. And he was starting to come up with a mathematical treatment for it, but that math treatment only applied to 1-electron systems. So then you even have a little bit past this, just to bring back some of the ideas of what you might see. And this ties in a little bit what's coming. You remember how you could draw Rutherford or Bohr-Rutherford images? So for instance, let's say you had oxygen, and we know that oxygen has a number of 8, therefore 8 electrons. So you'd have a plus 8 nucleus. In the first Bohr-Rutherford orbit, remember how they said you could draw in 2 dots, right? And then in the second, this is almost like a model or diagram to track the precursor to electron configuration, if you will. Then remember when you fed in the second one, you're allowed to put 8 in here, but they said, okay, what we're going to do is we've got 2, we got 6 more to go, so you have to put them in at the hands of a clock, the 12, 3, 6, and 9. So now I'm at 4, 6, I need 2 more, 7, 8. So they had these rules of how you could draw it in, right? And then they would say, for instance, what if you had a hydrogen, 2 hydrogens? So then they're saying this is oxygen. And then these little diagrams, they could even set up a precursor to a really crude form of bonding. They could say, you know, here's hydrogen, which has a +1 nucleus. And in its first orbit, I'll use an X for its electron. And then over here, you'd have another +1 hydrogen. Look, there's H2O, the bonding model to draw on paper. So what we have here, folks, the one thing that's indisputable is the atom, definitely in many of these things, has a highly concentrated dense nucleus, positive character. That's where the protons and even neutrons sit. And then around it, what's interesting is Rutherford, with this, not really even trying to draw a picture of the electrons as little BBs. He didn't do that. It's funny how this comes back in a way, because the quantum model calls this region electron density. The quantum model does not view it as if, like these little BBs that are always present, whirling around, and even worse, to talk about a specific orbit, these are horrible images in the quantum model. Strangely enough, this spread out, you know, electron negative charge stuff in his Reisenbund model is actually a little closer in some ways to the quantum model. So that's an overview of where we are today. I am not in the course going to hold you to the Bohr change in energy differences in his math description. No, not at all. But what I am going to introduce now before we head into the quantum one is, and I'll just flip this over, I am going to introduce one thing. This is a giant star. This is super, super important. Once, what we're going to be heading into, which is indisputable, the coming quantum mechanical model that I'm going to cover, first of all, the zeroth law is you have to have, again, 4 electrons. This is a chemistry course, and in quantum mechanics, almost all of the intro level stuff, the little particle that we always like to talk about first and foremost is electrons. Okay? This can be applied to stuff that's inside the nucleus or any other tiny particle if you want. But we're going to focus on electrons. So let's just say the type of thing that we're going to try and put in a cage, box, containment, putting physical spatial constraints, boundary. So what I'm saying is one of the zeroth concepts of quantum mechanics is going to be, if you're looking at tiny particles the size of an electron, and in chemistry we're focused on that because of bonding and electron configuration, all that jazz, you want to put that electron inside of a little cage, a little box, some form of containment that's holding it in, some constraints you're putting on the electron, and the boundary condition on all of these things. You have a little particle in some sort of container, containment constraints. That is crucial. If you don't have this versus infinitely free electron. So just the very idea that you have an electron that is not inside of any constraints, any containment, any boundary, any box, any cage, any kind of word like that. Infinitely free, an infinite space, and it's just there. What quantum is basically going to say, or question, at least say, you know what? I actually don't think we could observe anything distinguishable or an observable outcome. Quantization is very much the idea that the boundary conditions or the constraints of the cage, the circumstances of the box that a particle like an electron is trapped inside of, without that, you're not going to be able to observe pretty much anything that's distinguishable to be observed, period. So this is huge. And then what we're going to move on to is there's 2 things that even the summary in your book does make pretty much direct comment to, which is, at the end of the day, the only things we seem to know by experimental results, we actually measured it and seen it for ourselves, versus the new quantum mechanical complicated math framework spits out 2 things, which experiment definitely confirms. And that is, any system where a tiny little particle, such as an electron, is contained, bounded. When that occurs, you get simply separate energy states, number 1. And what we measure experimentally is the changes between any of the 2 energy states. We can accurately measure and we can calculate it quantum mechanically, and it matches experiment better than any other theory that's ever been constructed. So literally all you know for sure is there's allowable energy states for the system you're looking at. And number 2, in the case of an electron, if that's your particle, you get electron density, configuration, distribution, spread outness, delocalization. So these are key words that quantum mechanics can give you a very clear indication. It's almost as if this is basically going to say the electron becomes the orbital. So what you're going to be seeing very shortly is, for instance, you've seen them. If you have some sort of nucleus and they say that the 1s orbital, right, and you have an arrow that's pointing at this shaded area saying, for instance, if this was hydrogen in a 1s orbital, we can calculate the energy of the orbital that the electron, when the system has when the electron's in it, okay? We can calculate the energy of the next orbital if we chose to give it that energy, so we know the energy differences. And then number 2, this is the shape of the electron density, and people will tell you that the 1s orbital, the electron literally becomes this. And when you're not looking, or you're not interacting with the system, the electron literally does exist in what at the moment they're saying is this is not directly observable. They are 100% sure that a little BB image of an electron, and that little electron is always at all times remaining as a chunk of mass moving, cannot be true. It's almost as if in this system, the latest quantum field theory, it's the idea that this electron turns into something we can't observe directly. It is no longer a little BB moving around. It's spread out, distributed in the shape. This is a probability density of where you could find it. Every time you interact with the system, it would be like this. If somebody says, okay, every time you look in the system, you're going to find the electron, put a dot where you find it. Okay, I looked the first time, then I looked the second, then the third, then the fourth. Do this a trillion times, you get this color-coded density that shows where you found it, maybe a few outliers. So for an orbital, they're going to say, look, we're going to draw a line around where 90% of the time we find it. So leave these outliers out. So this is the image of a 1s orbital. And every time you look away, they even mathematically can calculate the time required for the mathematical wave function to return back to the spread out thing that it is. When you collapse the math function, you collapse the spread outness of the electron, which was the whole orbital. You collapse it to one observable result for that instant. This is the thing that we're going to have to get used to. This is the type of thing you're going to have heard said quite a few times. And we'll go over that a little bit more. So this is sort of an overview of kind of where we were, the key words of quantum mechanical theory, if you will. Some of the key, these are super key words. And the only two things that at the end of the day, quantum mechanics and even experiments show us are these two things.